hybrid models? Hybrid models achieve both higher accuracy and efficiency by combining the complementary strengths of transformer and state-space models such as Mamba 2. Transformer provides strong language modeling capability, while Mamba 2 offers high efficiency. However, these two corners differ significantly in their compute characteristics, which introduces new challenges. First, the performance bottleneck shift depending on the sequence length. At short length, Mamba layer dominates, but as the sequence grows, attention layers take over. These shifting behaviors make it difficult to maintain consistent performance. Second, even on modern GPUs, the compute utilization remains low. Despite kernel level optimization, flash attention saturate at around 61%, and SSD corners from Mamba 2 reach only 27% utilization. In other words, the current GPU leaves a large performance gap unexploited. The key challenge is clear. Hybrid models face shifting performance bottlenecks and low compute utilization under current GPUs. Let's take a step deeper into the hybrid model architecture. A typical hybrid model includes a few attention layers with several Mamba 2 layers. Therefore, to accelerate such hybrid model efficiently, we have to focus on two main computation corners: attention for transformer and state-space duality, or SSD for Mamba 2. Attention captures global dependencies, compensating the information loss of SSD, but it is computationally expensive. On the other hand, SSD is efficient, controlling how each input tokens updates fixed size states over time, but it suffers from gradual information loss due to the state decay. First, to optimize attention computation, flash attention 2 has become the most popular approach. It divides attention computation into small blocks and fuses key operations like QKT, softmax, PV within a single kernel, significantly reducing DRAM traffic. However, it still follows a synchronous design, preventing overlap member and no-member operations. So Flash Attention 3 redesigns Flash Attention 2 using Hopper-specific features. It introduces asynchronous two-stage pipelines and tensor memory accelerator, or TMA, for partial overlap. Since no-member operations such as softmax have much lower throughput than member operations on modern GPUs, so this partial overlap can improve the performance. Although Flash Attention 2 and 3 achieve higher arithmetic density, they are still underutilized even after GPU optimization. As the sequence length increases, both 800 and 800 GPUs are saturated at 61%, showing that only software-only fusion cannot reach this utilization solution. The reason is that Flash Attention is synchronous design, and Flash Attention 3 still suffer from register pressure due to the large intermediate data despite a synchronous two-stage pipeline. Therefore, we need a new data flow that enables true fine-grained pipelining, not just fusion. Now let's move on to Mamba 2 and its core algorithm called SSD. SSD reformulate the SSMs as semi-separable matrix, allowing partial parallelization of recurrent computations. And then SSD is decomposed into diagonal and off-diagonal blocks. Specifically, diagonal blocks compute local SSM output within each block, while off-diagonal block propagate and integrate states across the block. For processing diagonal and off-diagonal blocks in parallel, SSD is implemented using 5 GPU kernels. First, chunk Houston kernel reflects the decay of input and states over time with cumulative summation. Second, chunk state kernel computes local states of each block. And state classic kernels update each block states considering decay to produce final states. And VMM chunk kernel processes batch member for diagonal output. And lastly, chunk scan kernel computes both diagonal and off-diagonal blocks and combine them to produce final output. Even though these 5 kernels maximize the parallelism in SSD computation, SSD is still heavily memory bound. As shown in this graph, SSD shows low arithmetic intensity and under intermediate data that is not immediately reused. So SSD needs their reuse enhancement via Fusion. However, Fusion backfires. Our Fusion version SSD increased the latency by 1.74 times. So why did this happen? Each clock generates excessive intermediate data, and this causes register spilling and lower competency, degrading performance. Moreover, unlike flash attention, fused SSD involves both row-wise and column-wise dependencies due to its recurrent state updates, which forces sequential execution. So Fusion alone is not the answer. Based on previous analysis, we need block-level fusion with fine-grained pipelining, which improves compute utilization while reducing the intermediate data size. However, current GPU cannot efficiently support it yet. Their simply works assume uniform resources, failing work specialized pipelines with heterogeneous states. Also, TMA only supports coarse-grained transfers. Therefore, a specialized hardware is essential. This motivates our solution, HRX, a data flow hardware co-design that achieves consistent and high performance for hybrid models. HRX is designed with three goals. First, visual shifting bottlenecks for consistency. Second, maximize utilization via fine-grained pipelining. And third, provide unified hardware for both transformer and Mamba 2. We realized this goal through two new data flow, PyFlash and PySSD, and a new hardware core called Unified Reconfigurable Streamline Core, or URC. So let's first see the PyFlash. PyFlash applies row-wise fine-grained pipelining, overlapping softmax and output updates with QKT and PB computations. So this has minimal latency and reduces intermediate data by 4.58 times and boosts compute utilizations. Next, PySSD. First, we propose fused SSD, which fuses sequence length dimensions computation while maintaining head and X dimensions similar to flash attention. Second, we decompose this fused SSD into three pipeline stages, considering dependencies. First stage is pre-processing of DA, second stage is Y diagonal computation, and third stage is construct of Y off diagonal and state computation. Third, we apply fine-grained pipeline to these three pipeline stages. This reduces DRAM access by 6.8 times and intermediate data by 11 times, leading to significant speed up and utilization gains. Now let's look at the hardware side. So HRX employs a unified pipeline architecture that seamlessly supports both PyFlash and PySSD. The key component is the URC, which integrates three types of processing engines. First, the dot product engine, or DPE, performs the main matrix operations like manual and 1D convolution using 32 lane by 8 DPU structure. Second, reconfigurable vector processing engine, or RVPE, handles softmax and element-wise operation and processing for PyFlash and PySSD. Lastly, the update engine, or UPE, aggregates outputs such as Y diagonal and off diagonal and updates contention output and recurrent states. Together, these engines enable a fully pipeline execution for both potential and SSD components. Let's see how PyFlash and PySSD are mapped to URC. For PyFlash, for attention computations like QKT, softmax, PB, out and out updates are mapped on each processing engine sequentially. And for PySSD, the second stage computations for Y diagonal are mapped to URC sequentially, similar to PyFlash. And for the third stage computations that concurrently processing Y off diagonal and stage computation, RDP starts element-wise operation first, and then transfer the output to each DPE. Finally, UPE aggregates and updates the final output. This streamlined mapping achieves high utilization and smaller intermediate size. Now let's move on to the evaluation setup. So we evaluate HRX using a 2.7 billion parameter hybrid model from official Mamba 2 GitHub repository, which serves as the backbone for various hybrid models. for the TPU baseline, we developed a custom cycle level simulator that emulates TPU for history. To benchmark HLX, we developed a custom cycle level simulator and synthesized HLX in 14 nanometer process at 625 MHz. Finally, all results are evaluated across sequence lengths from 1K to 128K and batch size from 1 to 128. Here's the results. So HRX delivers up to 97% utilization for application computation and 78% for SSD computation. That is an average improvement of over 1.8 times and over 2 times compared to GPUs. Also, compared to TPU, HRX achieved about 10 times and 11 times compute utilization improvement. HRX shows large gain on TPUs because TPUs are optimized for dense memory operations, making them less suitable for memory-intensive SSD operations. And in terms of kernel latency, based on compute utilization improvement, HRX delivers about 2.8 times and 5 times speed up over GPUs. And it also delivers about 10 times, 11 times speed up over TPUs. For end-to-end, HRX achieve about 2.1 times speed over 800 and 5 times speed over TPU. So across all sequence lengths, HRX consistently outperform the GPU and TPU. Even when we scale batch size from 1 to 128, HRX achieve about average 1.5 times end-to-end speed up over GPUs. So this shows that a unified pipeline design adapts well to both small batch and large batch scenarios. So in this talk, I focus on the core contribution and the main vision. So for those who are interested in deeper analysis, our paper provides extended discussion. So please refer to the third paper. So to wrap up, HRX is the first unified accelerator for a hybrid transformer Mamba language model. And it co-designs data flow hardware to maintain consistent and high performance for hybrid models. High attention computation dependencies with fine-grained pipelining, and Pipe SSD introduces fusion-based pipeline SSD for better data use. And URSC executes both efficiently on a single hardware board. So as a result, HRX achieve up to 2.1 times speed up, end-to-end speed up, and 1.8 times speed up under batch workload, and while reducing area and power by up to 79% and 42% respectively. Thank you for kind attention.
Any questions from the audience? I have a quick question. So it looks like you are unified architecture. I do not remember this actually unified. If you assign something, yeah,
URSC.
So it includes the heterogeneous multiple different type of the processing elements. So in such a case, the one difficulty is actually maintaining the well-balanced pipeline stages. So do you have any know-how how to maintain?
So actually, there is a good question. So actually, I prepared some appendix for pipeline stage balancing because it is too important for our design. So actually, HRX balance the pipeline stages by aligning the throughput of DPE, RDPE, and UPE. So actually, fused SSD has a lot of, even though fused SSD has a lot of element-wise operation, but actually, fused SSD also has some matrix multiplication. And as you can see in this figure, so DPE actually has a large area, occupy large area and consumes large power. So actually, we first make some standards with DPE and matching the throughput with RDP and UP. So there's a, so we control flexible role-based balancing ensure high compute utilization and scalable across diverse Mamba configurations such as